to the Foamy Fizzy Fluids in Houdini tutorial. In the previous video we worked with our foam points to create some bubbles for us to render. In this video we'll go over how to mesh our liquid points into a geometry that we can render for our liquid, as well as creating additional fizz elements at the top of our liquid. So to start off, we're going to go back up in our network to where we split off the foam from our other points. So back on this delete, where we isolated our foam, I'm just going to copy this node, and I'm going to change the operation type to delete selected, so we're deleting our foam points. And I'll just change the name of the node to isolate liquid. So now these are only our liquid points. And then again, just for organization's sake, I'll also copy this null and rename it to liquid. So now that we've isolated our liquid points, we can start meshing them. And there are a few different ways to do this. Everybody kind of has a preferred method. What I'm going to go with is I'm going to use the particle fluid surface node. So plug that in and display it. And the reason we're not seeing anything is because it has a particle separation value, and this value needs to match the particle separation of our simulation. So I'm going to go back into our simulation and just copy that. So hop on in, go to our flip object, find our particle separation. I'm going to copy the parameter, and then I'm going to paste the relative reference. So that way if we go back and tweak our simulation at all, it'll update with whatever particle separation we were using. So now you can see we have some geometry up here. So now if we scrub through, we can see that we're getting a nice mesh of our liquid points. And I'm also going to change our output to surface polygons rather than surface polygon soup. And then let's go ahead and play blast that and see how it looks at default. You can see we've created a basic mesh of our points. We're getting a bit of jittering and lumpiness overall, and we can tweak that in our node. Luckily we don't need to worry too much about the lumpiness on the very top of the fluid, since that will be mostly obscured by our foam. So I'm actually going to go over to where we've isolated our foam particles, and I'm going to add those to our template selection, so that way we can see where they are in relation to our liquid as we mesh it. So I'm just going to hold shift and template it, so now we have those points in addition to our liquid, so we can see where they are in relation to our mesh. So if we scrub to the end, we can see that the foam points are going to definitely be covering a lot of our mesh. And back on our surfacing node, there's a few things we can tweak to help with the overall jittery and lumpiness we're getting. One thing I'm going to reduce is the adaptivity. If we drag this slider, you can start to get an idea of what it is this value is doing to our mesh. Basically, it's trying to have an adaptive need for the size of the polygons of our overall mesh. So it will create larger polygons for areas that are more uniform, more smooth along the edge, and smaller polygons for areas that have small detail. And I'm actually going to reduce this some, so that it's creating a mesh that is more accurate to the points that we simulated. So I'm going to reduce it to 0.001. So now you can see we have a pretty dense mesh, but I want to make sure I'm saving all of that detail that we put into our simulation. And then to help with the overall lumpiness that we're getting, I'll go over to the filtering tab. And there are a couple different things you can do here. I'm going to check on the smooth function. And you can see if you check it on and off, it's adding a nice little bit of smooth to our overall mesh. And what this is doing is inside of the particle fluid surface node, it's using a VDB from particle fluid node. So a VDB is being created inside this node. And checking this on is just adding a smooth function to that VDB. Generally, when you use the smooth function on your VDB, you might also want to dilate your VDB. So that way it's expanding slightly before you smooth it. You're not visually losing volume of your mesh. This also makes a pretty big difference for the beginning of our simulation, where there's some smaller tendrils of liquid that are flying up from the pretty turbulent motion. And you can see if we uncheck the smoothing, the edges of the tendrils are a little bit rounder and look a little uniform and kind of cartoony. But if we turn on the smoothing, it helps to bring those down in size a little bit. You can also adjust the amount of smoothing And you can see it'll start to break your geometry if you pull it way too high. You can start to get a little bit of a jaggy look because it's just smoothing, it's over smoothing it. So I'm just going to leave this at the default value of 2. You can also use different types of smooth operations, but I'm just going to use the mean curvature flow. So let's go ahead and playlist this and see how it looks now. So now you can see we've got a lot less lumpiness in our overall fluid mesh. There's still a little bit of jittering as it moves along the surface of the glass, but it's a lot less noticeable than it was before. And again, now that we've templated our foam points, we can see that we don't have to worry too much about any jittering we're getting on the top of our fluid. This is kind of up to personal preference. You might want to go back to the node where we were deleting stray particles in a previous video and delete the particles that are creating these smaller droplets, unless that's something you want to keep in your simulation. Same goes for shapes like this. It's possible you might not like the overall shape that you're getting with your little tendrils, and you can blast those points to get rid of them. But I'm pretty happy with the general look of our simulation, so I'm not going to blast those. The next thing we want to look at is if we zoom in, we can see that the mesh of our fluid is actually intersecting with our glass object, and that's going to be a big issue if we let it render like that. So we're going to want to make sure there's not intersection between the liquid and the glass objects. The way I'm going to do that is just with a boolean. So I'm going to put down a boolean. I'm going to use our particle fluid set to subtract a minus b. Then I'm going to plug the other connection up to our glass object. I'm going to put it in our poly extrude. Let's go ahead and visualize that. You can see that while it's cut out the fluid that was intersecting with our glass object, it's also turned all of these polygons black, and that's just because of a disparity in the normals. If you were to preview the normals, you can see that through our Boolean operation, we've lost all those normals from our fluid surface. And fixing this is as simple as putting down a normal node. So we'll just put that down, connect it in, display, and you can see everything's working as expected. Another thing to take into account is that the geometry created from our Boolean is matching the geometry of our glass. So there is a huge difference between the overall surface of the edges of the fluid and the top of the fluid now. So we're going to want to remesh the result of our Boolean. And doing that is pretty simple. So we can just go back to our Boolean node, and if you scroll down, there's a section for output primitive groups, and we're going to output the B inside A group. And then we're just going to put down a subdivide. And we're going to change the group to B inside A. Now you can see that we're only subdividing the geometry that was cut by our Boolean operation. You can go ahead and increase that subdivision. So now you can see there's not a huge disparity between the topology of the top of our fluid and the sides of our fluid. Using the Boolean operation did create a couple gaps in our liquid where you can see the seam of our Boolean, and those are pretty easy to fix as well. Just put down a fuse, and we're going to reduce the snap distance since we're working at a pretty small scale. Let's do it to just big enough to fix those points. So just kind of play with the value until it's fixing the points we need it to fix. Let's do 0.005. So now you can see that those holes are being merged together. If we go back up to our particle fluid surface node, you can see that it actually tries to transfer our attributes for us, and we can visualize them to see how they've been transferred. We scrub through, you can see we have our velocity values, but we've broken those much like with the normals when we did our Boolean. Those velocity values were lost. So much like our foam bubbles when we made them into geometry, we're going to have to transfer over our attributes from our points back onto our final mesh. So to get those back, we're going to use an attribute transfer again. So we'll just put down an attribute transfer. Going to transfer to our geometry from our liquid points. And there's a few different attributes I want to grab. First I want to grab the velocity so that we have it for motion blur at render time. I want to grab the vorticity. This is going to drive part of the shader of our liquid. And I also want to grab the age. And we'll go ahead and preview that. And I'm also going to put down a visualize. This way we can check that our attributes are transferring as expected. So over on our visualizers, I'm going to change the attribute we're looking at to velocity, so just V, and change it to a ramped attribute. And then I'm just going to put down a switch so that we can take a look at how it compares to our original points. So now we can just switch between the two to see if the attribute looks like it's the same between the two. So that looks like they're matching up pretty well. We can do the same for vorticity. You can see that's matching up. And age. And that seems to be matching up as well. So with our attributes transferred, we can go ahead and cache out our surface mesh. And I'm just going to go ahead and copy one of the other file caches we've made. And just drop it down and rename it. So I'll just call it liquid surface render. And then I'll cache it out. Now that it's cached out, I'm just going to put down a null. And I'm going to call it out liquid surface so that I know to grab this when it's time to render the liquid. Alright, the next element we're going to work on is the fizz that emits from the top of the fluid. In this slow motion reference, you can see the fizz that I'm referring to. It's made up of tiny particles of fluid that are being forced out of the drink as a result of the compressed carbon dioxide gas that's pushing its way to the surface. We want to replicate this really small popping motion in our scene. In our reference, we saw the fizz emitting from the surface of the liquid. So we're going to replicate that in our scene. So to do that, I'm going to work with the geometry that we just cached out. And I'm going to isolate the top area where I want the fizz to emit from. I'm going to do that by putting down a group node. And I'm going to display that. I'm going to name the group top. I'm going to check off the base group so that not everything is automatically in the group. And I'm going to enable keep by normals. So what this does is it creates groups based on the normals of the primitive. So if we pan around, we can see that right now if we change the spread angle, we're getting primitives that are facing out along the z-axis. And that's based on this direction value. Let's go back to our camera view. We're going to need to change this direction value so that we're getting the primitives that are on the top of our fluid. So I'll put this to 0. And I'll set this to 1. And adjust the spread as needed. Now you can see that I'm isolating these top faces based on their normal, and they're adding to the group called top. And then with that group created, I'm just going to put down a delete. And I'm going to select our group, and I'm going to do delete non-selected. So now we just have the top of our fluid. So I'm going to remove the template flag I have on our foam points so that they aren't distracting us. So now we're just templating the glass. Now with the top of our fluid isolated, I'm going to put down a scatter. And the reason I'm doing this is because I'm going to create a pop network to emit particles from the surface, and these points are basically going to be the source for those particles. For now, most of the default settings on the scatter are fine. I'm just going to change the global seed. I'm going to change it to $T. That way the seed is reliant on the current time in our scene, so there's a little bit more variance between the scattering of the points on each frame. After that, it's as simple as putting down a pop network. This is a lot like just creating a dot network, but when you specify a pop net, it will automatically create some of the nodes for you. Let's go ahead and jump on in. So let's take a look at what the pop network has created. It's created a basic pop object for us, a pop solver, as well as a pop source, and a merge node in case we had multiple sources. And we don't have multiple sources, so we can go ahead and delete that. Now let's check out our pop source. Right now we don't see anything in our viewport, and that's because our pop source is using the first context geometry and scattering points on the surface. And while we do want it to use the first context geometry that we plugged into our pop network, we are using points. We don't need it to try to scatter points. So we're going to change the emission type to all points. That way it's using the points that we've already created. So now if we scrub through our timeline, you can see that we're getting points emitted from the geometry. And they're kind of flying everywhere, super erratic, and that's because the geometry they're emitting from has an inherent velocity. If you'll remember, we made sure that our fluid mesh had velocity values, and the points are automatically inheriting that. So to fix that wild motion we're getting, I'm actually going to go over to the Attributes tab of our pop source. And rather than using the inherited velocity, I'm actually going to change it to set initial velocity. So that way we have more control over the velocity as the particles are created. I'm going to set their velocity to be pretty low. We don't need them to move too far in space. So to start off, I'm going to change the variance value to 0.1 in each direction. That way the initial velocity is plus or minus 0.1. And if you scrub through, you can see that the particles are not flying out nearly as far. And then I'm going to add velocity in the y-axis since we expect them to move upwards. So I'm going to change this to 0.15. So now you can see the particles are moving up as well as moving outwards. And the next thing you'll notice is that these particles seem to kind of move forever. They don't die off, they're just continuously moving outwards. And the reason for that is on the birth tab, you'll see that their life expectancy is 100, and this refers to 100 seconds, and we definitely don't need them to live that long. So I'm going to turn the life expectancy down to about 0.15. And I'm going to change the variance to 0.05. That way, not all particles are dying at the exact same time. So now if we scrub through our timeline, you can see we're still getting a nice motion of them emitting outwards and upwards, and they're dying off. Another thing I want to address is you can see that we're getting particles emitting from the initial pour of our simulation. And much like the foam, I don't expect to have this fizzy interaction happening right when we're pouring our liquid out of the bottle into the glass. I just want the fizz to emit from fluid that has already been in the glass for a little bit. So to do that, I'm going to go back up above our simulation, and I'm going to put a wrangle down between our delete and our scatter. And much like our main simulation, I'm going to create a group that is based on the age. So I'm just going to create a group, let's just call it new, and set it to 0. Then we'll do an if statement. So if the age is less than 0.4, then those points will be in our new group. So now we can just put down another delete, and we can select our new group, and then we'll change the entity to points since it's a point group. So now if we scrub through, we'll see that we're not getting the geometry of the new points. Next thing I want to do for our pop simulation is to bring in our glass object for a collision. And that's pretty simple to do since we've already set it up for collision in a different simulation. So we can just go back to our main sim, and we can simply copy our glass object back into our pop network and paste our static object. And we can just merge it into our simulation, keeping in mind that we want it to be on the left side of our merge node so that it affects our points. So now you can see we've got our glass object. I'm just going to switch to wireframe so we can see our points. And if we scrub through, you can see that the fizz is not starting to emit until the liquid has already been in the glass for a little bit, and it's also interacting with our glass as expected. Even though we've reduced the overall velocity of our points, they're still moving a little bit erratic for my taste. So I'm going to add a pop drag. This will basically create some air resistance for our particles to give them a little bit more realistic motion as they move through our scene. So let's go ahead and run a play blast to get a feel for how this looks. So you can see we have a nice upward motion of our fizz. It's moving pretty quickly, which is pretty true to life. There are a couple things I want to address in our current setup. The first being that we have a lot of points. We probably can reduce the amount that we're scattering before we go into our simulation. And we're also getting some points down here at the bottom. So let's go ahead and get rid of these problem points as well as reduce the overall amount of points that we're using for our fizz. Let's go back up above our simulation to the scatter node. And I'm actually going to set some keyframes for our scatter node. For our simulation, I expect the fizz to emit from our fluid and kind of increase initially, have a lot of fizz coming up as the fluid rises and the foam rises, and then it'll plateau, the fizz will be a little bit consistent, and then it'll wind back down as the fluid settles. So I'm just going to go around to a couple different frames and set the force total count and set some keyframes. So I'm going to set the initial one to 0. And I'm going to Alt left click to set a keyframe. I'll go to frame 30 and turn it up to 1500. Let's just go along through here. And then just keep this value the same, so that's where it's kind of plateauing. Then I'll go all the way to the last frame and set this to 0 so that it's winding down. If we shift left click on this channel, we can see the animation editor. We go ahead and fit this into our current view area. You can see that we kind of have the motion that I was talking about, where we'll start off with no fizz, it'll quickly build up to do a lot of fizz, and then start to plateau out before reducing overall. If we scrub through our timeline, we can see we're still getting these little problem points down here at the bottom. One quick way we can handle those is to simply delete points that are beneath a certain value in the y-axis. Since we aren't emitting fizz until the liquid is already in the cup, so the fizz is not at the very bottom of the cup where those problem points are, it'll be fine to go ahead and just set a hard and fast rule that all the points below this y value should be deleted. So we can just do that real quick with a delete. Let's go to a frame where we can see those problem points. So down here, change it to points, and we'll set it to delete by expression. And we'll just put in an expression here that refers to their position in y. Now you might remember from our main simulation when we were ramping a force based on the position in y, our lowest value in y was 0.09. So we can just do at p.y is less than, let's do 0.09 initially. So we can just increase this slightly until we're grabbing the points that we need to grab. And we'll just scrub through to make sure we're not deleting any points we don't want to delete. So now that we've gotten rid of those problem points as well as adjusted the overall number of points that are emitted over time, let's go ahead and take a look at how our simulation looks now. So now you can see we're not getting any of those problem points, and the amount of fizz is changing over time. It's a little hard to see towards the middle because of how densely packed our points are, so we can change our display settings so that the points are smaller in our scene. I'm also going to turn off this blue guide on our pop source. So let's go ahead and turn off that guide. And then in the viewport, if you just hit D, you can go over to geometry and then point size. So we can scrub through so we have some points on screen. So I'm just going to reduce it to 2 so they're a little bit smaller so we can get a little bit better feel for how many points there are. One other thing I noticed in our Play Blast is that the fizz points just kind of pop off. They just die based on that life value we set. And while that's fine, it kind of feels like they're just going up into space and disappearing. And I'd like to give them a little bit of a falling motion, a little bit of a feeling of gravity just before they die, so that we get the sense that the particulates of fluid are rising up out of the fluid mesh and then falling back down. So to do that, I'm going to put down a pop force and plug that in. Now just using a normal gravity force would be close to -10 in this value. But that would be a little too strong for our scene, so I'm just going to set it to -4. Let's go ahead and see how that looks. So immediately you can see that the force is working in our scene, but it's affecting the particles immediately. Right when they're born, they're getting that initial velocity we set, but this new pseudo-gravity velocity is immediately pulling them down, so we don't get to see them popping out of the surface. So I'm going to add an expression to our pop force, so that this new force doesn't immediately affect particles right when they're born. So on our pop force node, we'll just check on use vexpressions. And then much like we've been doing throughout this tutorial, we're going to use the age. So we're going to say if the age is less than 0.1, the force will multiply by 0, and finish with the curly bracket. So this is saying if the age is less than 0.1, which is a pretty small value, so just when they're initially born, they won't be affected by this negative value. So let's see how that looks. Alright, so now you can see we're not having our particles immediately pulled down when they're born. We're still getting a nice feeling of particles falling before they die. Now that we've got a pretty nice simulation for our fizz, we can go ahead and cache it out. So we'll just go back up to our DOP network. And I'm going to go over to the object merge on the DOP network node, and I'm just going to put the word pop before object. So this way, when you're displaying the DOP node or hooking in a file cache to the output, it will only grab our pop object. Otherwise, it would also grab our static object, and we don't need to grab that. So we can go ahead and grab one of our file cache nodes and rename it. FizzSim VO1. Should also name our DOP network. Just call it FizzSim. And then we can go ahead and cache this out. And then, much like our micro bubbles for our foam, we're going to be rendering the fizz as points. So to preview the current p-scale and get a feel for what we're working with, I'm just going to copy over those nodes we were using with our micro bubbles. So let's just go over here. We'll grab the sphere, copy to points, and the randomized p-scale. We'll just make copies of those. And we'll just plug in our points from our FizzSim. So if you scrub through our timeline, you actually can't see anything. And the reason for that is if we middle mouse on our FizzSim, and we look through the attributes, you'll notice that there's not a p-scale attribute. P-scale is something that the FlipSim automatically created for us, but when we just create a pop network, it doesn't automatically create a p-scale for us. So what we're going to do is on our attribute randomize, instead of multiply, we're going to change this to set value. So now if we scrub through, we can see we have enormous pieces of geometry because this value is pretty big for a p-scale. So fixing that is as simple as reducing the global scale. So I'm going to turn it down quite a bit. So now if we scrub through our timeline, we can get a feel for how our fizz is looking. That's pretty good. I'm noticing a couple stray points that have popped outside the glass, and we can easily remove those with the ID trick we were using before. So we can go ahead and just display on our P-scale, and we can just grab those points. So back into select mode, point select, and turn on groups at ID, and we can just grab these points that are sticking out of our glass. Let's scrub through, see if there's more problem points, and just kind of grab them as you see them. And then once you've grabbed all of them, you can simply hit delete. So that way those points are no longer an issue. And now that we have those points set up, we can just put down a null. So I'm just going to copy the null that we used from our foam, plug that in, and just rename this out fizz. So now we have our foam, both geometry bubbles and micro bubbles, as well as the mesh for our liquid and some additional fizz detail all ready to go to render. In our next video, we will tackle our last layer of the effect. We're going to create some bubbles that rise up inside the liquid, as well as some bubbles that are stuck along the surface of the glass.